All right. I'm Gary Tan from the Pennsylvania State University. So this is mostly the work of my student, Xiaodong, who cannot be here because of visa issue. Okay, so our paper is about grammar inference. So here we have a black box program, and we want to learn a grammar for inputs to this program. And for example, if the program takes a set of inputs like XML strings, we want to infer a XML-like grammar. Okay. And grammar inference has lots of applications from understanding programs to reverse engineering to grammar-based fuzzing and many others. So we study this problem under this active learning setting. So in this setting, we assume we have Oracle. It has an internal grammar G we want to learn. And we can submit two kinds of queries to the Oracle. So in the membership query, we put the input string S to the Oracle. And if S belongs to this grammar G, then the Oracle returns yes. Otherwise, the Oracle returns no. Then in the equivalence query, we can submit a hypothesis grammar G prime to the Oracle. And then if G and G prime are equivalent in the sense that they represent the same language, then the Oracle returns yes. Otherwise, the Oracle returns no. And in that case, the Oracle also returns a counterexample showing inequivalence. So we note that equivalence queries can actually be approximated by membership queries. That's what we do in our implementation. But for the simplicity of this talk, I'm going to assume the existence of equivalence queries. So there has been excellent work in this area. First, there was this seminal algorithm called L-star for learning regular grammars and many follow-up work. And there was also a good amount of work on learning context-free grammars, including recent work, Glade and Avada. So their limitation is they have limited accuracy for many practical grammars, and I will come back to this when we discuss evaluation. So in our work, we try to improve grammar inference accuracy by exploiting something called nesting structures. So what is a nesting structure? Let me go through an example, XML string. So in this example, we start with this open tag P, and then followed by this string hello, and then followed by this close tag P. So two observations here. First, open and close tags must be matched. And also, open and close tags can be nested with arbitrary depths. What that means is if we repeat this open tag P at the beginning and the close tag P twice at the end, then it's still a valid XML string. So is the case if we repeat P 3 times at the beginning and 3 times at the end, and so on. So at the grammar level, this nesting structure actually implies some kind of a recursion, right? So for example, to model this kind of XML strings, we can imagine a grammar rule like this. We have this non-terminal L, then it starts with some open tag, then followed by L, which recurses to itself, then followed by a close tag. All right. So nesting structures are widely used in languages and formats. For example, for XML and HTML, we have open and close tags. For JSON, we use open and close curly brackets to enclose JSON objects, and use open and close square brackets to enclose JSON arrays. And in Lisp, we put S expressions inside the parentheses. Right? So our hypothesis is we should be able to exploit nesting structures to improve grammar inference. And for that, we employ a special kind of grammars called visibly pushdown grammars. So a VPG here is really just a regular grammar plus nesting structures. So VPG grammar explicitly marks open and close tags. And in the VPG, open tag is called a call symbol, and the close tag is called a return symbol. So that's the language I'm going to use. Here's an example VPG rule. In this example rule, A is a call symbol. And the rule explicitly tells you it's a call symbol by marking it with this left angle bracket. And then B is a return symbol, and it's marked with this right angle bracket. So I also know there has some prior work on learning VBGs. However, the limitation is they assume call and return symbols are known ahead of time. Okay. So our work called VStar is the first VBG learning algorithm without assuming call and return symbols. So we propose this nesting test for inferring call and return symbols. And on top of that, we develop a L-star style algorithm to learn a special kind of visibly pushdown automata. And we also have techniques for inferring a partial tokenizer. So on top of that, we develop meta theory. We have theorems about correctness as well as when VStar can achieve active learning, exact learning, sorry. And then we also develop comparative evaluation and show we have more accurate results than related algorithms. Okay, now let's go into some details. Here shows the major steps of VStar. So the inputs include an oracle as well as a set of sample strings. We call them C strings. Then the first step is to infer call and return symbols. And after that, VStar learns a visibly pushdown automaton. And then we convert that VPA into a visibly pushdown grammar. Okay. So next step is to discuss how to infer call and return symbols. And for that, we formulate a VPG pumping lemma. So let me explain that. So in this lemma, suppose we have some string S belongs to this VPG language L. Then if this S is sufficiently long, then there must exist some substrings X and Y, okay? So that if we repeat X and Y an equal amount of times, say K times, to construct this new string S prime, then it must be the case that S prime must also belong to this VPG language L for all K greater than or equal to 1. In addition, X must contain a call symbol, and Y must contain a return symbol. Okay. So that's the VPG pumping lemma we formulate. And based on this lemma, we can actually infer call and return symbols. But first, let me give you a quick example using the same string we looked at earlier. So for this string, X is just the open tag P, Y is the closed tag P. And then if we repeat X and Y twice or 3 times or K times, the resulting strings are still in this XML language. Okay, so that forms the basis of our algorithm for inferring call and return symbols. For C string, we identify so-called nesting patterns. So a nesting pattern is just a pair of substrings X and Y, so that if we repeat X and Y an equal amount of times, we get a string in the language. And however, if we repeat X and Y unequal amount of times, we get a string not in the language. Then by the pumping lemma, then we know X must contain a call symbol, Y must contain a return symbol, right? Based on these nesting patterns, we can formulate an algorithm. The idea is, in the first step, we search through all C strings to identify all nesting patterns. And then we are going to do a search on those nesting patterns to identify possible call and return symbols. So in the end, it computes a so-called compatible call and return tagging. A compatible tagging just ensures each nesting pattern has a call and return symbol. So the detailed algorithm is in the paper, but that's the spirit of the algorithm. And on top of the algorithm, we develop some meta theory. First, we show the algorithm terminates and it's correct. And we also have a theorem saying that for Oracle VPG language L, there exists a finite set of C strings S0, so that call and return tagging compatible with nesting patterns in S0 must also be compatible with nesting patterns in every string in this VPG language L. So this shows that it is sufficient to fit a finite set of C strings S0 for this call and return inference. Okay, so after we learn call and return symbols, so the next step is to learn a visibly pushdown automaton. Our algorithm actually adapts L-star for learning a DFA. So let me explain that algorithm quickly next. So in this L-star algorithm, in each round we maintain 2 sets, Q and T. And Q is a set of strings. Each string will be converted into a state in the DFA later on. Then T is a set of test strings. In this case, it's a set of suffix test strings, which are used to test equivalence of strings in Q. We maintain two properties of Q. Q must be separable, meaning that for any S1, S2 in Q, it must be the case that S1 is not equivalent to S2 according to test strings in T. So this relies on this congruence relation to show S1, S2 are not equivalent according to test strings in T. Then Q also must be closed, which means for any S in Q, if we append a character C to the end of S to get SC, SC must be equivalent to some S prime that's already in Q. Okay. And then if Q is separable and closed, then we can construct a hypothesis DFA based on the strings in Q. And then we can submit an equivalence query to the oracle. And then if the oracle says it's equivalent to the internal grammar G, then we already found our DFA. Otherwise, the oracle returns a counterexample. The counterexample is used to update Q and T to get Q prime, T prime, and the process continues, and also the process terminates. All right, so to learn a VPA using L star style algorithm, we actually learn a special kind of VPA called a K single entry VPA, where K stands for the number of K symbols. In a K single entry VPA, we actually have K plus 1 modules. Each module has a single entry. The 0th module is a main entry. And then whenever we encounter the ith call symbol, the control is transferred to the ith module. And then whenever the ith return symbol is encountered, the ith module returns to the caller module. So in the running of the VPA, you need to use a stack to remember the encountered call symbols so that you can return to the caller. Okay. So that's called a K single entry VPA. And we adapt L star algorithm for learning a K single entry VPA. So we have to generalize many definitions here. First, a test string in T now becomes a context string with both a prefix and a suffix, not just suffixes as in L star. We also have to generalize congruence relations for a K single entry VPA, and also with updated definitions of separability and closeness. Then we adjust we also need to construct a procedure for constructing a VPA using Q and T, as well as updating Q and T using a counterexample S. Okay, so all the details are in the paper. On top of the algorithm, we developed this exact learning theorem. Basically, it says the minimal K single entry VPA for VPG can be learned in a polynomial number of membership and equivalence queries. Okay, so there's a lot more in the paper, including how to convert a visibly pushdown automaton to a visibly pushdown grammar, and how we combine the inference of a partial tokenizer with VPG learning. So this turns out to be necessary in practice because many practical languages coordinate return symbols are at the level of tokens instead of the level of characters. And we also discuss in the paper how to approximate equivalence queries with membership queries, as well as other details. Okay, next, let me quickly go over the evaluation. So we replicated the artifacts in Avada and Glade's evaluation, which included Oracle grammars, data sets, and C strings. And we chose a set of grammars including JSON, Lisp, XML, and a couple of other languages. So this table shows the accuracy evaluation between V-star and Glade and Avada. We use standard metrics, including recall, precision, and F1 scores. As you can see, for these grammars, V-star actually achieved perfect learning, and its accuracy is substantially higher than Glade and Avada. So this showing that by exploiting nesting structures, we get much higher accuracy. Okay, so this table is a comparing the efficiency between V-Star and Glade and Avada in terms of the number of membership queries and the total time. As you can see, V-Star actually takes a lot more queries and time for the learning. So the major reason is in V-Star we approximate equivalence queries using membership queries. So that takes a lot of membership queries to finish. And also in V-Star, we have this partial tokenizer. We try to infer a partial tokenizer using membership queries, while Glade and Avada relied on heuristics to tokenize the inputs. But in any case, there's clearly room for efficiency improvement for V-Star. We do note that in grammar inference evaluation, we think it's more important to evaluate accuracy than efficiency because in many practical situations, grammar inference can be done offline and just need to be done once. Okay, so some quick conclusions. V-Star is the first VBG inference algorithm without assuming call return symbols. And for that, we propose a set of novel techniques, including nesting patterns, L-star style algorithm, and also the inference of a partial tokenizer. And on top of that, we develop meta theory for algorithm correctness and exact learning. And we also developed the comparative evaluation showing our algorithm is more accurate at the cost of more time. So our artifact is available online. And at the end, I also plug in some shameless advertisement. Our lead author is on the job market, and my research group's also looking for a postdoc on probabilistic program verification and software security. Thank you for your time.
All right, yeah, we have time for some questions.
Thanks for the great talk. I have been working on the similar grammar inference problem for a while. So in fact, we developed the tool Trivada that appeared in ICSI this year. I was very fascinated about how you infer the call return symbols, right? Mm-hmm. So what if the call return symbol, it also exists within the body that enclosed by these tokens? For example, let's say you have a string surrounded by quotes, and the quote also exists by escape characters. So how would you infer those call return token in that case?
So I think in that case, you would have to break that token into subtokens, right? So, and say a particular subtoken is a call symbol and another subtoken is a return symbol, then you make that kind of match in our framework. Yeah.
Okay, I got it. Another question about, have you analyzed about how prone to like different kind of seed sets? Mm-hmm. Because we felt that when we make some changes on the seed sets, like use a different set of seeds, it performs differently. So have you analyzed like trying with different seed sets?
Yeah, actually that's a great question. I think this kind of algorithm is sensitive to seed sets, as you pointed out. So in our case, to infer call and return symbols, we found you really need a seed to witness all possible recursions in a grammar. Actually, I showed this theorem for showing that there exists a seed set for sufficient learning, right? So, and to construct that seed set, you actually, in the proof, we actually have to enumerate all the possible recursion for all the non-terminals in the grammar. So essentially, that means if a seed set witnesses all the recursion, then it's okay. But of course, the question is, whether the seed set can cover that. Okay, that's a great point.
Okay. Thank you.
Yeah.
Hi, thank you. Very interesting work. I'm curious about performance that you talked about at the end. Mm-hmm. So I'm curious if learning the call and return symbols mm-hmm. is a particularly large part of the performance degradation. I'm guessing that it is, since it's what's especially new from the other work. I don't know if that's something that you looked at or not. And I'm especially curious if you think that there might be any way in the future, so this is maybe an idea for future work, to make use of approximations mm-hmm. somehow as part of that. Like you could approximate with a regular grammar or a dike grammar or something like that, and then maybe recover the call and return symbols more efficiently?
Yeah, it's a great point. Actually, in the paper, we do have a breakdown of the number of queries we use for inferring call return symbols versus learning the VPA. Actually, it depends on what grammar you are learning. So it turns out for most grammars, it takes more time to learn the VPA than inferring call and return symbol. But there was actually a grammar where the majority of queries were about learning, were about inferring call and return symbols. So yeah, I think there is definitely opportunities for efficiency improvement. That's something we are looking at. Yeah, happy to discuss more. Okay.
Thanks for the great talk. I was curious, what happens if you give V-star a grammar that is not visibly pushed down?
Yeah, actually, I think it can still produce something. Okay, it just might not be something you expect. So I guess there are two parts, right? First, does the grammar have some kind of matching structure? And if it does, then you can still infer those matching structures, right? Then the second problem is even if it has some matching structure, it may not be a VPA, right? So then the grammar, our V-star will still learn something, but it may not have the guarantee we stated in the exact learning theorem. Okay.
That's really cool. Thanks.
I had a question. Thank you for the talk. I had a question about like second and third slide where you say that the inputs, you have the oracle, but also you have some strings. I was wondering, why can't you just start from the empty string if you are using the feedback from the oracle to make new strings? I may be misunderstanding something.
Yeah. So I think that oracle is mostly for learning the VPA, right? So, and we also need to kind of also infer call and return symbols. So it turns out the C strings are necessary for kind of richness recursion at the grammar level, so that our algorithm can actually ask the right membership queries. So if I put it that way, but the details are in the paper, we can talk more offline. Yeah.
Thank you for the next speaker can set up while you're answering the last question.
Yeah, maybe a little bit related to this
Sure.
last question.
Sure.
Could you give a little bit of intuition? How do you select informative queries for the approximation of the equivalence queries from the membership queries?
Yeah. So what we do is, I think we are not the only one doing this, is we take those C strings and then break them down into suffixes and prefixes, then combine them, and then in different ways then submit those combinations as membership queries to approximate equivalence queries. So that's what we do for this implementation, which turns out to work pretty well.
Thank you.
All right. Let's thank Gary again.